the integer formed by reversing the digits of n. Okay, for example, the number is 25. The reverse of this number will be 52. All right, and subtracting 52 from 27, we get, all right, from 25 we get 27, minus 27 actually, and the absolute value of that is 27. So it is majorly a implementation problem. So the major requirement of this problem is to know how to calculate the reverse of a number. Okay, so let's learn it. We want to find, okay, what do we want to do to find the reverse of a number? Like, we had a number like this, we pick up the last number from uh, last digit from our number and put it inside the new number, claiming that it is the first digit. All right, this particular process gives us the reverse of our number. So pick up the last digit, write it down in the bottom, and then remove it. Now again pick up the last digit, write it down in the bottom, remove it. Do this process unless and until there is at least one digit remaining in the number. All right, and at the end, through this we got the reverse of our number. So let's write it down in the form of a code. So how would we implement this? Initially the reverse would be 0 because there was nothing written in the bottom, and the upper number was equal to n. Let's say we have a number I which represents the number written in the upper part of our text that we wrote just now. Now what did we say? Continue the process up until uh, there is at least one digit remaining. Okay, and then remove the last digit. Now we want the current digit, that is last digit in, okay, in this process we want the last digit, that is we want 3, and insert it at the end. Okay, how to get the last digit of a number? Just reminder with 10 gives us the very last digit. Okay, so I reminder with 10. Now insert it in the end of reverse. All right, so how to insert it inside the end? Like we have 5 and we want to insert 3 to make it 53. So what do we do? Multiply 5 with 10 and then insert 3. All right, just do the same. Reverse multiplied by 10 plus digit. At the end, what do we need to do? We need to return the difference between, absolute value of difference between n and the reverse number. That is it. We have implemented the first problem. Let's move to the second problem. In the second problem, we are given a string s of length n and integer array cost of same length, where cost at ith is the cost to delete ith character of s. You may delete any number of characters from S such that the resulting string is non-empty and consists of equal characters. Okay, what do the questions say? The questions say that we have a string given to us and each character has a cost corresponding to it. The cost is given us in the form of a vector, and to remove that particular element or character, we must inculcate that particular cost given to us. Now at the end, we want a string which consists of only a single character, that is only consisting of B, only consisting of A, or only consisting of C. That is only a single character should be present at the end. Now we are asked what is the minimum total deletion cost required to form such a string. Okay, so at the end, what do we have? Only a single character. All right, and uh, what are the possible scenarios of final string? let's say our string was made up of, how many characters are there in English alphabet? 26. So they are made up of all 26 alphabets. So at the end, it might either contain all the A's that were initially present. Let's write it down. Observations. Only 26 characters. The end must contain all the occurrence of a given character. Why should it contain all the occurrence of given character? Let's say we had three A's and at the end only A remains. Okay, some string and one more A. At the end only A's remain. Then we have to remove all the characters other than A for sure. And if we remove one extra A, then we are inculcating an extra which can be saved. All right, so it's better not to delete uh, a when at the end only A's are remaining in our string. Now, what is the third observation? Okay, the third observation is all the characters except the chosen one are removed. Okay, so since there are only 26 characters, maintain a of map of cost, map of character, and cost of removing all the characters, all the occurrence. All right. What do this mean? Like we want to remove all the A's from our string. So this particular A has cost 1 and this particular A has a cost 2. So sum of all these values uh, need to be contained in this map. Why so? Because at the end, if uh, only A's remain, okay, then, okay, how many number of characters are there? Only 26 characters are there. So how many possible scenarios? 26 scenarios. Iterate over all the scenarios and uh, say that the current character is the character that remains at the end. So what is the cost for that? The cost is uh, total number of characters or total number of cost minus. What is total number of cost? Cost of erasing all the characters in our string. Okay, sum of all the cost minus what do we have at the end? We have all the A's remaining. All right. So cost of removing all A's. What did we say? We just remove all the characters and inculcated this particular cost. But we say, hey, we could have only A's remaining at the end. So what is our saving in that case? All the cost that belongs to A. So total number of cost minus the value that is present inside our map. So this is our logic. Let's implement it in the form of a code. Okay. So what did we say? We want a map of character comma int. Now iterate over all the indices and add its cost inside our map. Now we also want the total cost. All right. The total cost is added by this cost again. Now at the end the uh, we want our savings to be maximum. Okay, so to maximize or minimize this particular value, the minus term, because this particular thing is constant and we want our total term to be minimized. So this particular term should be maximum. So take maximum of all the possible scenarios in which a character remains. So I iterate over all the elements of map and take the maximum, because we are using long and our map. Uh, okay, let's make our map long okay, as well. This saves us from errors while comparing elements. Okay, at the end, what do we want? We want to return the final value. What is the final value? Total cost minus the maximum cost. Minus mx. Okay, that is it for this problem. Let's move to the next problem now. So the problem is minimum swaps to avoid forbidden values. The problem says that you are given two integer arrays, nums and forbidden, each of length n. You may you may perform the following operation any number of times. Choose two distinct indices I and j, swap nums at I at and nums at j, return the minimum number of swaps required such that for each index I, the value nums I is not equal to forbidden at I. If no amount of swaps can ensure that every indices avoids its forbidden value, return minus 1. Okay, what does the problem say? The problem says that we are given two arrays, nums and forbidden. Let's say nums is this and forbidden is this. Note that this nums is not a permutation, but it's a array. Okay, it is written down here, the constraint of nums and forbidden. And it is also not guaranteed that all the elements occurring in nums occur in forbidden. Okay, so what do the problem say? We need to apply swaps in nums. So what do a swap mean? It means choose two indices and swap their values. That is, choose first and third index, swap their value. Okay, this is a swap operation. And what does the problem say? Apply some swap operation such that at the end, none of the nums value matches with the corresponding forbidden value. That is, at index I, if nums at I is equal to x, then forbidden at I should not be equal to x. Alright. And we want the minimum number of swaps to do so. And any more constraint? No, that is it. So let's move to some of the observations. What is the first observation? Okay, let's say the indices with nums at I equals to forbidden at I are denoted by, okay, that's are denoted by forbidden from now. Okay. So what are the forbidden indices? Really sorry for delays. Now start. Indices with nums at I equal to forbidden at I are denoted by forbidden indices from now on. For example, here the second index num set 2 is equal to forbidden at 2. That is, the index 2 of nums is equal to 2, and forbidden has value 2 at index 2 again. So these two values are equal. So it is a forbidden index. Now what is our first observation? If we swap okay, what is our aim? First of all, our aim is to reduce the forbidden indexes, reduce the count of forbidden indices to 0. Okay, now if we swap two forbidden indices and they are swappable, what do we mean by swappable? Like we have 2 comma 2 and 2 comma 2 again. So these two indices are forbidden. Like let's say we have an array of size 2 and array is like this. Num sets this and forbidden is this. Then these two indices are not swappable for sure, because if we swap both of them, then again both of them will be forbidden. So if two, there are possible scenarios where we can swap, like swap this 2 with this 3. Okay, because this 3 is not forbidden, let's create an example where we can swap two forbidden indices. Let's say, just let's have the same example. Here we had 1 and 1, and here we have 2 and 2. Okay, these two are forbidden, and if we swap both of them, it will be 2 1, and this will reduce the count of forbidden indices by 2. So if we swap two forbidden indices, count reduces by 2. Okay, if we swap one forbidden index with a non-forbidden index, count reduce by 1. So what will we want? We will want greedily. Okay, we will greedily want that we apply the first operation every time, because it reduces the count by 2, and we want the minimum number of swaps. Okay, here we are applying one swap and count reduces by 2, and here we are applying one swap and count reduces by 1. So applying this operation gives us the scenario where the count reduces uh, in a larger amount. So the total number of operations will be lesser if we apply the maximum number of first operations. All right. Okay. So keep a count of all the forbidden indices. Try to maximize the number of swaps among them. Okay. And for the rest remaining, if we come to a conclusion that there are some indices, forbidden indices, which cannot be swapped among themselves, like here we had 2 and 2, they cannot be swapped among themselves. Okay, so swap them with non-forbidden indices. and at the end, if it is possible, then return, if possible, return minimum number of swaps. If it is not possible, that is the remaining forbidden indices do not have a corresponding non-forbidden indices that can neutralize them, then return -1. Okay, so let's have a construction of swapping the forbidden indices, which gives us the best answer. Okay, okay. First observation from now onwards. How many observations have we done so far? Two. So this is the third observation. What is the third observation? If the count of forbidden indices is odd, one will remain. Okay, just keep this in mind. We will use this later on. Now, let's say count. Okay, now how can we represent this? There are some forbidden indices that cannot be swapped among themselves, and some forbidden indices that can be swapped among themselves. For example, if we had two twos and one one, then this would be a different group. The group containing all ones would be different because okay, we will discuss later on. And the group of all twos will be different. Why? Because among a group, two numbers cannot be swapped, but intergroup, that is group 1 and group 2, they can be swapped among themselves. Okay, so create groups corresponding to the value of forbidden indices, and inside the group the swaps cannot happen, but outside the group, that is intergroup swaps, are always valid. Okay, now let's think about the scenario where uh, we will have to apply the second type of operation. Okay, that is swapping forbidden index with non-forbidden index. When will we have such a scenario? Let's say we have five twos. Okay, and 1 3, 1 4, 1 5, and 1 6, and 1 7. These all are forbidden indices. Then we can swap this 3 with this 2, this 4 with this 2, this 5 with this 2, and so on, because it is a good construction, that is start applying the operation with the forbidden index with maximum frequency. Okay, why? Because at the end, the element with maximum frequency has the highest probability of being left over. Okay, why? Because let's say if at the end 3 is left off and all twos are uh, completed, all twos have completed their swapping, then there is a construction, all right, that do not swap this 2 with the leftover element, and rather swap the leftover element with this 3. So start swapping with in the decreasing order of frequency. And what do we observe here? We observe, like, okay, let's have an analogy to understand this scenario. Like let's say in a group, let's say there is a group 2 with 5 soldiers, and currently because we want to fit in all the twos, then the opponent group, all the numbers other than this group becomes their opponent. Then the opponent group will have total number of elements minus the number of elements in this group. So it is equal to 5 again. Opponent group also has 5 elements. Now, uh, if these two groups fight among themselves and one soldier can kill only one soldier, so all these 5 soldiers will kill each other, and at the end 0 elements will be remaining, and that is what we want. Okay, we want the swaps to happen in such a scenario that no element is left at the end, while if this group has much larger elements, that is group 2 has 7 elements and the opponent group has just 5 elements, then whatever construction you make, these 5 soldiers cannot defeat these 7 soldiers, because one soldier kill only one soldier, only, okay, neutralize one soldier. So there will be the number of elements in group 2 minus the opponent group, that is 2 elements remaining at the end in any possible construction. Okay, and what is the third scenario? They, in group 2 there are only 2 elements, and in opponent group there are 5 elements, so 3 soldiers will be left and continue the same process what we have done uh, recursively. Okay, and at the end all the swappings would be done unless and until only one element remain. Okay, so let's write it down. If current group has more elements than the rest means all the opponents, then current minus rest elements remain, else all the swaps can be done. All right, and keep in mind that if the forbidden indices have a odd count, one will remain for sure always. So how can we use this for our uh, for solving our problem now? So we are currently at a position where we have removed all the swaps which could be done using the first operation. The first operation that reduces the count by 2. Now we are left over with those elements where a forbidden index needs to be swapped by a non-forbidden index. Now, how can we do so? Iterate over all the non-forbidden indices and check if a swap is possible. And if a swap is possible, swap it. Else, continue. At the end, if we have a count more than the number of leftover soldiers we had, then swap is possible. Add one to our one for all those swaps and two for the swaps within the forbidden indices, and that will be our answer. So let's write it down once. What will be our implementation? First, we will try that we apply operation of type 1. Swaps within forbidden indices. How many swaps are possible? Then we will apply type 2. Okay. How many swaps are possible? It is equal to the maximum frequency minus rest of elements. Okay, and if it gives a negative number, then 0 will be the number of forbidden indices left over for type 2. And for type 2, just do brute force. That is, check over all the indices that if a swap is possible or not. Because anyway, one one operation or one count will be reduced. So brute force works here. So this is our logic. Let's move to the implementation part. Okay. So let's create a vector. Vector will store all the indices of forbidden indices. Okay, all the index number, that is, forbidden index is present at, okay, forbidden element is present at index 2, index 5, index 7. So all these indices will be stored in this vector. Okay, now iterate over all the elements of nums. If the current element equals the forbidden element, just push the current index inside our forbidden indices. All right. Now create a map which gives us the frequency of all the forbidden indices. Okay, because we wanted the element with highest frequency. Okay. So iterate over all the forbidden indices and insert it inside the map. This index has this value and this value has this frequency. Hello, I think the internet is fine now. So let's start. Okay. If the current forbidden index or forbidden element's frequency is greater than, it will become the maximum, and the value corresponding to the maximum is at the end, what is the total number of forbidden indices? It is equal to the size of our vector that we created. And what are the leftover elements? The leftover elements will be comma maximum minus n minus maximum. What is this formula? We discussed maximum frequency minus, hey, hello, okay, so I think the issue is fine now. Okay, so the what are the leftover elements? We discussed this in the formula. maximum frequency minus rest of the elements. What is the rest of the elements minus the current element? Okay, so these are the leftover elements. Now, as soon as we know that the leftover elements are equal to 0, we can return n plus 1 by 2. How? Why n plus 1 by 2? Because we said that for odd count of forbidden indices, 1 will remain. Okay, let's understand it with an example. Yeah, this internet issue. I think we are good to go now. So we were discussing an example where we are left over with odd number of forbidden indices at the end. Okay, so for example, this scenario itself, if it was 3 rather than 2, so we would have swapped these two elements. Okay, because we are doing a maximum number of swaps within the groups, and 2 was a group and 1 was a group, so we swapped these two groups to get 1 and 2. Now this is the leftover element, so swap it again with one of the elements that we have already swapped over, one of the groups. So what happens here? 3 and 1. So this gives us a valid answer. Alright. So how many number of swaps are required? N by 2 for elements except this one. Okay. N by 2 for elements except this one. And 1 extra for this element itself. So n by 2 plus 1 or n plus 1 by 2. Because n plus 1 by 2 for even gives floor, and for odd it gives 1 extra. Okay, that is what we want. So n plus 1 by 2. So now currently, what are the count of indices at which we can perform the second operation? What is the second operation? One forbidden index and one non-forbidden index. I iterate over all the indices and check if it is a forbidden index or not. If it is a forbidden index, then just continue. Else, if check for the validity of swap. After swap, what should be the possible scenario and what should not be the scenario? The bad scenarios would be forbidden at the swapped element is equal to the element which we swap, that is val, or this should not be there, and one more thing should not be there, that is the value that is present here currently should not be equal to forbidden value of the swapping element, which is val again. Okay, if this is not a scenario, then it is a valid scenario, and add 1 to our cur, that is one more valid index is present which can be swapped with a forbidden index. At the end, if cur is greater than equal to left, return n minus left by 2, because we were doing plus left. For this part, that is n minus left, we did swapping operations, all right, within the group. So n by 2 number of operations were required. For the rest, one operation were needed to be required because count reduces by one only. So this is it. At the end, we need to return something when there is no answer possible, and it is written in the problem that we need to return -1 in that case. So this is it for this problem. Let's move to the next problem and the last problem for today. The problem name is total sum of intersection cost of tree groups. Okay, we are given an integer n and an undirected tree with n nodes numbered from 0 to n minus 1. This is represented by a 2D array edges of length n minus 1, where edge at I is equal to ui vi indicates a undirected edge between nodes ui and vi. We are also given a integer array groups of length n, where group at I denote that group label assigned to node I. Two nodes u and v are considered part of same group if group of u is equal to group of v. The intersection cost between u and v is defined as the number of edges on unique path connecting them in the tree. Return the integer denoting sum of intersection cost over all unordered pairs u comma v with u not equal to v, that group at u is equal to group at v. Okay, what does the problem say? The problem say that we have a tree. Let's create a tree for visualization. Okay, this is the tree. Now, all of these nodes are given some group number. Let's say this is one. This belong to first group. This belong to first group, and this belong to first group. So, for all of the pairs, that is, first pair is this node, and this node. Second pair is this node and this node. Third pair is this node and this node. Okay. For all these three pairs, the yellow pair, calculate the distance between them. It is 1, 2. Now for the pair, for the red pairs, what is the distance between them? 1, 2, 3, 4. For the green pair, what is the distance? 1, 2. Okay. So for group 1, the total distance is for red one. Okay, for yellow one it is 2. For red one it is 4, and for green one it is 2 again. For red one, okay, for red one it is 4. For yellow one it is 2. For red one it is 4, and for green one it is 2 again. All right. So over all the groups and all the pairs in that group, we need to find the sum of distances. All right. So how can we do so? First of all, let's move to the constraint. The value of n is 1e5. So we can run a DFS or BFS with a log n or log n square, something like that. And what is the value of groups? The value of groups is at most 20. Okay. So we can iterate over all the groups and run DFS. This idea comes from the constraint itself. Okay. Now, if we can solve for a given group, then take the sum of all the values, and that is our answer. Okay. What did I say? Just for example, here we calculated for group 1. All right. And the sum comes out to be 8. Now, do we do the same for group 2, do the same for group 3, and so on up till group 20? The sum of all those sums, that is 8 plus the answer due to group 2, answer due to group 3, that will be our answer. All right. So, our problem is reduced. New problem. We have some marked nodes. Find find the distance between all the pairs of marked node. Okay, this still is a n square problem. Why? Because a particular group might have at most n number of elements, and iterating over all the pairs is still n square. So we need to reduce the problem even more. Let's consider an idea. Consider a contribution due to each edge instead of consider a contribution due to each edge instead of iterating over all the pairs. What do this mean? What do this mean? For example, let's consider this edge. All right, this particular edge. Let's say this edge. How many times is this edge considered in the distance between some pairs? Okay, how many times it is considered? It is actually considered 2 times, one due to red and one due to yellow. How can we confirm this thing? Okay, if there is a node present to the left of or in the subtree of this edge. Okay, in this part, if there is a marked node, then this marked node will uh, create a pair with other marked nodes to the other side of this edge. Okay, and how many times will it create? 1 times for all the numbers present to the other side of this edge. Okay, so this gives us the idea that for each edge, the contribution in shortest path is equal to the number of elements in its subtree times number of elements not in its subtree. This is a very visualizable thing. Let's visualize it once again if you have problem. Okay. For example, you have this scenario. Okay. Now, how can we say this? Okay. There are two classrooms. Okay. In the first classroom, there are n students, and in the second classroom, there are m students. Now, each person from class 1 goes and handshakes with each person from classroom 2. So how many total number of handshakes will be there? Okay, for every person there will okay, every person from class 1 will stand and go and do m handshakes for each person. And how many times this is happening? N times this is happening because there are n persons. So total number of handshakes will be n into m. Okay, similarly, it is happening here. There is a breakage which denotes two classrooms or two groups. In the first group, we have one element, and the second group, we have two elements. So total number of contribution to this particular edge will be equal to 1 into 2. Now, let's calculate for a scenario to just uh, satisfy ourselves whether this particular answer is correct or not. Okay, this edge is contributing how many times? 1 into 2 times. How many times is this edge contributing? This edge is contributing again 1 into 2 because in the subtree, one element is present, and outside the subtree, these two elements are present. So 1 into 2. Now coming to this particular edge. Okay, how many times is this contributing? Uh, to the subtree of its, one element is present, this one. So 1, and outside the subtree of it, two elements are present, this one and this one. So it is 2. Now again for this particular edge, how many times it is contributing? 1 into 2. What is the final sum? The final sum is 2 plus 2 plus 2 plus 2, which is equal to 8. And that was our initial answer. So we have come up with a construction where we can find the number of uh, handshakes, or let's say number of pairs, and sum among all those pairs for a given group. Now at the end we need to sum up for all the groups and just return it as an answer. So the leftover part is just an implementation problem. So let's move to the implementation. So we are given the graph in the form, or a tree in the form of uh, edges. We want a adjacency list, so create a global adjacency list so we can pass it later into the DFS for iterating over all the edges. Okay, now we want to store the sum over all the groups. Let's say we store it inside a variable name answer. We also want to have the total count of marked edges for each group. So for each group, let's have marked. Okay, now just assign these data structures some values, or initialize them, let's say. There are at max 20 groups. So assign it 21 size. Now iterate over all the edges. Just created adjacency list using this. Now iterate over all the groups, and we want the marked to contain the total count of marked nodes. So marked of G plus plus. Now initialize the answer value as 0 again. Now iterate over all the groups. How many groups are there? From 1 to 20. Run a DFS for counting the contribution due to each edges. Start it with node 0. Say that its parent is -1, and I denotes the group number and also pass the group array. So we are writing down the DFS. Now what will the DFS return? The DFS will return the number of marked nodes in subtree of a given node. Okay. Let's say this is the node, this is the parent, this is the group, and we also passed vector group. Okay. Now current number of marked nodes in its subtree is 0. Now if this particular node itself is a marked node, then its group equals to the desired group. Then increment the counter by 1. Now iterate over all of its children. If neighbor equals to parent, then continue. Else count plus is equal to the number of marked nodes in its child. Okay, we want the number of marked nodes in its subtree. So the current node plus number of marked nodes in its child. At the end, number of handshakes is equal to the number of elements in its child multiplied by the number of elements not in its subtree. Okay, number of elements in its subtree multiplied by number of elements not in its subtree. This is equal to total number of marked nodes minus the number of marked nodes in its subtree. At the end, return, not here. At the end, return, okay, return this count. That is it. Uh, this particular construction has given us an answer value and return that answer value. That is it for this problem. Let's meet the next time for next contest. All the best for then.